Today we're going to have a look at representing integers in MIPS. Now we should all know the difference between signed and unsigned binary notation, but it's going to be incredibly important going forward, so we need to have a little recap just so that we have a good strong grasp of the concept before we tackle more difficult areas. So before we get started, let's have a look at binary again. Now remember, the way that we convert from binary to decimal is that we take the value in a column and multiply it by its place value. So for example, here in the ones column we take 1 multiplied by 2 to the power 1. That goes into the summation and we add 1 to our total. And then we do this in every column until we have the final number. And it's also worth remembering that we count from 0 for bit numbers. So the first column is the 0th column. It's similar to arrays. But yeah, so another thing that's worth remembering is that with n bits we can represent 2 to the n distinct values. Now the largest value we can represent is 2 to the n minus 1. That's because we have to represent the value 0 in order to have a good full set notation. So again, yes, the more numbers that the more bits that we have, the more values that we can represent, the larger our range. And with 8 bits of unsigned integers, the largest value we could represent would be FF at 255, and 00 is the lowest, of course. Now there's an important crossover point here in the middle where 7F goes to 80, and you'll notice that that's because the largest bit, the most significant bit, gets set, and that's right in halfway in our range. Now why is that important? Well, that's important because of 2's complement. 2's complement is where we represent negative numbers in binary by using the leftmost bit, the most significant bit, to tell us whether or not a value is negative or not. So that leftmost column, you can think of it as representing 2 to the power 8 minus, and then we add everything else to that value to see what negative number we have. So for FF, we're adding everything to minus 2 to the power 8 to get minus 1 out. And why did we talk about that crossover period? Because that's where a number goes from being positive to negative. So 7F is the largest positive number we can represent, 127, and if we add 1 to it, instead of going to 128, that'll actually take us down to minus 128, so that's the most negative number we can represent with 8 bits in 2's complement notation. Yeah, and one way you can get the binary value for a number is if you take 2 to the power 8 minus k and subtract it, then you'll get the negative number in binary. So for example, if you do that with minus 1, 2 to the power 8 would be beyond the scope of what we have actually. But if you do 2 to the power 8 minus 1, you'll get every bit set, and that will be the representation of minus 1. So yeah, this should all be relatively familiar to you. One thing that's worth noting as a corner case is that the most negative number, minus 2 to the power 7, which is minus 128, doesn't have a corresponding positive number. So if you were to try and negate that, something weird might happen. We'll have a look at that in a moment, but it would be hard for you to go from minus 128 to the opposite number because there's nothing there. The closest you might have is 127, or you might just look back to yourself. Okay, now all of these concepts carry across to larger number of bits. So half words, again, the same applies. The same applies to words. We just have larger numbers that we can represent. So the reason why this is important is because in MIPS we have a choice as to whether we use signed or unsigned. So for example, here we have a lot of comparison operations. So we have set greater than or equal unsigned, set greater than unsigned, and so on and so forth. Why is this important? Because if you're comparing a number, it might look like you have a larger number and you're just setting up to compare, say if this one's greater than the other, but you might not realize that one of those numbers is negative, and you might think it's a larger number, but you don't get the behavior you want because when MIPS comes to check, it thinks it's a signed number, and so the larger number is actually just a negative number. So you have to be wary of when you choose to use the signed or the unsigned variants. And this is similar for branching instructions. So far we haven't really used them because we haven't really dove into this sort of complexity before. But it is worth noting that you need to make sure you know what behavior you want to encode before you start using branching instructions to make sure you get the right thing out. Okay, so to go back to negative numbers, the way that we invert a number, that is to take a positive number and get to negative, or vice versa, is that we invert the bits, so we flip all the bits, and then we add 1. So you can see here, if we have OC to start with, the 12, as its decimal equivalent. If we invert the bits, now you could do this either by negating or you could do it by toggling with an XOR. That would get you to minus 13, and so you have to add 1 to get to minus 12. And it's the same for 32 bits as it is for 8 bits. But one thing you should notice about this is the extension of the sign that's happening here. So when we negate it, we have a lot of ones set, and again, this might look like a large number if you're not keeping a coherent idea in your head of which you're using, signed or unsigned. But this will be something that comes up later. So what happens if we start with the most negative number? This is a corner case that you might want to try in MIPS actually, because you get some interesting behaviour. Because if we have the largest negative number, and there is no corresponding positive number, then what happens when we flip the bits? Well, we flip the bits and that takes us from 80 to 7f, which is 127. And then when you add 1, you come back to 80 again. So you come back to where you were. You've looped round, as it were, back to the value you started with. Now, I'd recommend you try this in MIPS. So load a value of 80 in, and then try and negate it, see what happens. It might not be what you expect, but it's something we're going to have to worry about coming in the next week. So, this is something we've touched on briefly, but it's something I wanted to go over in a bit more detail, is what happens when you load bytes without using the unsigned instruction. So for example, here we have 4 instructions of loading bytes. So if we load the byte unsigned into A0 from CocoCalc, CocoCalc has EA, which is unsigned 234, and signed it's minus 22. Now if we use load byte unsigned, it loads the whole word, because remember we need to fill the register with a word, so it extends the sign by 0. So we get a bunch of zeros, and it represents 234. However, in the immediate instruction after that, if we load byte instead of load byte unsigned with the same value into A1, it extends the sign bit, and because E is bigger than 7, it will definitely have its sign bit set, and it will extend that sign bit all the way down, so we get a much different value. This is why you have to be wary, because if you're trying to work with unsigned values and you don't use load byte unsigned, you'll have something that really messes with your program's behavior and its meaning. However, if we have a look at the last 2 examples, the value that we're loading there from CocoCalc D is 1C, which doesn't have its sign bit set. So these 2 instructions have the same behavior, and this is why it can be tricky, because you might get that in some cases it behaves as you expect it to. However, it might come into some later on part of your code where it doesn't do what you expect it to, and you have some sort of mistake coming in because you've extended the sign bit when you didn't want to. Okay, and yes, we've mentioned this before, but load byte unsigned treats it as an unsigned number between 0 and 255. Load byte treats it as a signed number and tries to keep that meaning and treats it as a number between minus 128 and 127. This is the same for half words. Again, we have similar examples here. We have, if we load the half word unsigned from CocoCalc, it's actually a negative number, but if we use load half byte unsigned, we keep the positive number, the unsigned version. If we use load half word, we extend the half word with f's to get the negative number that it corresponds to. And similarly, when we have a positive number that's positive in both unsigned and signed notation, it keeps the same value. And this is because similarly to load byte and unsigned and load byte, load half word unsigned treats it as an unsigned number, whereas load half word treats it as a negative number or a signed number and tries to keep that meaning intact. So this is where sign extension is at play. So you'll notice when you have load byte unsigned, load half word unsigned, their instructions give you this weird thing saying sign next and then int a 8a. And what this is saying is either we do sign extension or we use zero extension. What's the difference? Well, zero extension is we extend the word with zeros to fit the register, and this is what happens when you use load byte unsigned. Load byte unsigned just treats it as a number that's not signed and extends it with zeros. However, load byte, when it has a negative number, it will take the sign bit and it will extend it all the way to the end. Whereas if it has a positive number, whether it's signed or unsigned, load byte will just extend the 0 forward. So the sign extension, down at the bottom here you can see, it extends the bit that represents the sign. Whether that's a 1 or a 0, it will extend it, whereas the unsigned value variants, they don't extend, they just extend, or they do extend, they extend with zeros, but they don't replicate the sign bit. Similarly, there's signed instructions for shifting right and shifting left. These are the arithmetic versions, but we don't really want to worry too much about these. These extend the values, well, when you extend right, they extend the sign bit, and they also try to capture rounding, which isn't tremendously useful, so probably wouldn't recommend you use them. They might be useful in some cases, but you have to be quite wary of what you're doing to know when to use them. It's probably safer, I would say, just to use shift right unless you have a specific idea in mind. So when would we use signed versus unsigned? Well, we would use signed if we need negative numbers, of course, that's what they're for. That's when we would use them. We might want to use unsigned if we want to represent very large positive integers. And if we have small values, it doesn't really matter because we can represent a lot of values with a full word that doesn't have its sign bit set. So we could possibly get away with just using either in that case. And for non-numeric data, unsigned is probably what we want because we don't want it to try and enforce the logic of sign extension onto something that's not a number. That's everything I wanted to go over today. That's just a recap of stuff that we should hopefully know already, just to try and reinforce this before we tackle some of the concepts that will be coming next week. I hope you found this useful. If you have any questions about anything I've covered here today, please do let me know. Thanks.